Okay, so today we're going to be talking about nutritional ecology, and we're specifically going to look at protein leverage. Okay, well, first of all, I have nothing to declare. That was easy. Nutritional ecology is the science that looks between the link between what an organism needs to eat and what it gets to eat. It's basically what you need to eat versus what you get. It's kind of sad sometimes. We're going to use a tool today called nutritional geometry, which is a framework for how we look at different mixtures of nutrients influence biological outcomes. And the classic example of nutritional ecology is protein versus energy. This is what most scientists look at when they're talking about nutritional ecology. And by energy, I mean carbs and fats. So your foods can basically be thought of as protein versus energy, which is carbs or fats. So imagine you have an organism that has access to food that's mostly protein, like meat, and another food that's mostly energy, either carbs or fats. Now, this organism is going to have some sort of nutritional fitness target where it functions optimally. And what it's going to do is it's going to eat a little bit of one food, a little bit of the other food, a little of the first food, a little bit of the second food, and it's going to make its way to its fitness target by mixing together these two complementary nutrients. Now, every organism on Earth is doing this every day, and they don't even really realize it, but this is how it works. So on the left, you've got food one, which is a balanced food and goes right through your nutrient target. This might be something perfect for an organism to eat. You've got foods 2 and 3, which are complementary foods that can be mixed together in a complementary fashion to hit the organism's nutrient target. And then on the right, you've got, unfortunately, food 3, which is not a balanced food and does not hit an organism's nutrient target. And then your organism has to decide, well, am I going to overeat fat to get enough protein, or am I going to undereat protein to avoid eating too much fat? You're going to have to come up with a compromise. So in summary, a balanced food hits an organism's nutrient target perfectly. An unbalanced food that's complementary, you can mix together two different foods. Or you could have an unbalanced food that doesn't hit your nutrient target, and then you have to come up with a compromise, overeating something or undereating something. Okay, let's look at, just to get a flavor for what this protein leverage thing is, let's look at protein leverage in animal models. And we're going to talk today a lot about these two guys called Raubenheimer and Simpson, and they're sort of the godfathers of the protein leverage hypothesis. And these guys have been researching nutritional ecology for years in all kinds of animals, insects, rats, mice, humans, you name it. Here's one of their classic mice studies. And what they did is they took mice and gave them 5 different foods: a 9% protein food, a 17% protein food, 23% protein food, 31% protein food, 48% protein food. The mice mix all these together and they end up at about 23% protein, which is their self-selected macronutrient target. That's kind of where they like to be. Now, what happens if you lock these mice up into 5 different cages with these 5 different foods by themselves? Well, here's what happens. The 23% mice eat the exact same amount of energy. The 9% mice eat a lot more energy because they're trying to get enough protein, and the 48% mice eat less energy because they've already hit their protein target at a lower energy intake. This is protein leverage. You're looking at a graph of protein leverage. This is what it looks like. This is how we would graph it out. So these guys have done all sorts of macronutrient self-selection studies in all sorts of animals. Dogs like 30% protein, cats like 52% protein. They've studied this in freaking slime molds, which is a unicellular amoebic blob. You can surround it with different protein to energy ratios, and it'll go right for 2 grams of protein to 1 gram of energy every time, because that's its self-selected macronutrient target. Okay, primates. Primates exhibit a ridiculous amount of protein prioritization or protein leverage. Here's a study in monkeys. You see carbs plus fat, or energy, on the y-axis, protein on the x-axis, and tiny changes in the amount of protein eaten lead to huge shifts up and down in the amount of carbs and fat eaten. Basically, these monkeys are just eating to get enough protein. This is a graph of protein leverage. This is protein prioritization. This is what it looks like. You get this ridiculously narrow vertical line of protein prioritization. Now let's look at humans. Humans exhibit the same amount of protein prioritization, but we don't know it. We actually have no clue at all. For example, here's a graph of carbs versus fat in all the countries on Earth, and there's massive variations in carb versus fat intake on the planet. Way over here on the high carb side, you've got Nigeria and Japan and India. These countries are very high in carb. On the high fat side, you've got US, UK, Germany, France. All these countries are somewhere in between these extremes of carb and fat. But what you don't see is any variation in protein versus energy. Like every single population on Earth is locked into this super laser focus 14 to 15% protein all countries on Earth. This is protein leverage. This is protein prioritization. Humans don't know they're doing this, but their protein content is very, very tightly controlled. Okay, so we've all seen this graph before. This is obesity. Somewhere in the 70s, obesity just started taking off, and it's been climbing ever since. And you ask yourself, well, what was happening to the macronutrients during this period of time? And if you zoom in on the macros, you see that carbs and fat were going up. And this was basically protein dilution. We dumped a bunch of sugar, flour, and oil into the food supply. What happened in the 70s is we dumped in sugar, flour, and oil. We diluted protein, but you know we're going to eat to get the same amount of protein, so you end up massively overeating carb and fat to get there. Protein went up very slightly much later when we all had larger bodies. We were literally fatter, and we had higher absolute protein requirements, and only then did protein go up slightly. Now, I have to point out, when I said that fat went up during this period of time, that was specifically only in the form of vegetable oil, because animal fat went way down in the past 50 years. So basically, you have all the fat increase in the form of vegetable oil completely. So again, we have carbs going way up. We have fat going up only in the form of vegetable oil. And we have protein staying flat as a pancake. If you look at protein percentage, it went down slightly from 14% to 12.5%. So Raubenheimer and Simpson looked at this and they said, oh, well, we know exactly what this is. This is just straight up protein leverage. I mean, we've seen this in every animal on Earth. You drop protein from 14% down to 12.5%, you're going to get a massive increase in carb and fat intake. Tiny change in protein, huge increase in carb and fat. We've seen this in everything from insects to rats and mice and primates, and every animal functions this way. Makes perfect sense. The protein leverage hypothesis says that if you eat 1.5% less protein, you're going to eat 14% more carbs and fats to make up for it. Conversely, if you increased your protein by 1.5%, you'd eat 11% less carbs and fat. And Raubenheimer and Simpson ran the numbers, and sure enough, it adds up perfectly. You can easily explain the entire obesity epidemic by this protein dilution and this 1.5% decrease in protein. The numbers add up perfectly. Okay, now protein leverage is a real thing. This has actually been studied in humans. Here's a study in humans, actual live humans randomized to 5% protein, 15% protein, or 30% protein, and you see that the 30% protein ate just like slightly less than or more than half the energy of the 5% people. This is protein leverage in actual humans. It's a real thing. This is not theoretical. This is not a hypothesis. This is basically a proven fact. Now, Raubenheimer and Simpson did this amazing meta-analysis where they looked at every study they could get a hold of where humans ate ad lib amounts of food, meaning you ate as much as you wanted, but somebody was tracking their macronutrients. They found 155 studies where humans ate ad lib food with tracked macros, and they graphed it out. And here's what you get, this ridiculously narrow vertical line of protein prioritization, where tiny changes in protein lead to massive shifts in carbs and fat eaten. This is protein leverage in humans. You're looking at a graph of protein leverage. Nobody knows this is happening. This is totally happening. Raubenheimer and Simpson took all this data, all 155 studies, and made an ad lib energy intake heat map, which is totally fascinating. You've got the highest energy intakes from the far left in dark red, the lowest energy intakes from the far right in dark blue, and you've got protein percent on the x-axis. And what you can see is ad lib energy intake is 100% about the protein intake on the x-axis. Fat percent is on the y-axis, and going up and down in fat percent seems to have no effect at all in ad lib energy intake. There is a carbohydrate effect. Carbohydrates are coming down these diagonals from the upper right, and as you increase carbs, you do see an increase in ad lib energy intake, but protein's the main story here. Okay, I'm going to zoom out for a second and look at this from an evolutionary perspective. This is a study estimating worldwide hunter-gatherer macronutrient ratios, and I'm quoting from this study, this high reliance on animal-based foods coupled with the relatively low carbohydrate content of wild plant foods produces universally characteristic macronutrient ratios in which protein is elevated 19 to 35% at the expense of carbohydrates. What does this mean? If we dumped you off in the wilderness with a spear, you are not going to get any carbohydrates from wild, uncultivated plant foods. You're going to be on a very low carb diet. You're going to be killing animals nose to tail, and you're going to have a very high protein diet. It's going to be pretty high. Raubenheimer and Simpson unpacked this a little bit in their excellent book, The Nature of Nutrition. And on the far left here, you've got the Paleolithic, where we were not getting a lot of carbs from plant foods, and we had a very high protein diet, eating mostly animals. And then you have the agricultural revolution, where we figured out how to grow starch, and we diluted protein, and as a result, we were smaller, and we were less healthy. We had more dental disease, for example. And then finally, you've got the Industrial Revolution, where we figured out the bulk refining and transport of sugar, flour, and oil, and we dumped all these energies into the food supply and diluted the hell out of our protein, and now everybody's super fat. Okay, here's another study, another meta-analysis by Raubenheimer and Simpson, where they looked at, I believe, 38 different studies, again, looking at ad lib human energy intakes and tracking macros. And again, they've got energy intakes just completely linear with protein percent on the x-axis, with the highest intakes on the far left and the lowest intakes on the far right. And this time they asked themselves, well, does carbs versus fat even matter? Is there even a difference between carbs and fats? Is it really just all energy? Is it all about protein? And so they graphed out this data, and here is a theoretical, hypothetical graph you would get if carbs and fats were the same thing. They put carbs on the y-axis, fat on the x-axis, and this time protein on the diagonals. And if carbs and fat were the same, you would get this graph right here. That is not the graph that they got. This is a hypothetical, theoretical graph if there was no difference. This is the graph they got, which clearly shows a significant carbohydrate effect, where as you go higher in carbohydrate percentage, you have higher energy intakes. Interestingly, there's almost no fat effect at all. Both the highest and lowest intakes are right on top of each other there at about 40% fat. So there's a definite carbohydrate effect, and there's really not much of a fat effect here. They found the lowest ad lib energy intakes were at a super high protein percentage of 50%, moderate fat of 40%, and extremely low carbs of 10%. And when they zoomed in on this data, they made a really fascinating discovery. Below 20% protein, they actually did not see a difference between carbs and fats. They saw a difference above 20% protein, but not below it. And this is interesting because we know that all modern humans are eating below 20% protein, but all hunter-gatherer humans were eating above 20% protein. And then you've got modern obesity researchers saying things like, oh, carbs versus fat doesn't matter, it's just all calories, right? They're both the same, it's just calories, we're just looking at calories. But then you have we paleo types saying things like, oh, hold on a second, the more carbs I eat, the more energy I eat. And this interestingly supports the fact that maybe both groups are correct, and that in today's modern, abnormally low protein intakes, there's not as much an effect. I have to point out that this lowest ad lib energy intake occurs at 2 grams of protein to 1 gram of fat with very low carbs. What food looks like that? That's pretty much any kind of meat, right? Ground beef is 2 grams of protein to 1 gram of fat. You eat a whole chicken or a whole turkey or a whole cow for that matter. You're basically eating nose to tail animal. You're getting 2 grams of protein to 1 gram of fat with no carbs. Okay, here is Raubenheimer and Simpson's ad lib energy intake, and I have to point out that both the highest and the lowest ad lib energy intakes are the exact same fat percent of around 40% fat. Fat doesn't seem to even be a factor. It's just not a factor one way or the other. What we do see is this huge protein and carbohydrate flip-flop, where the very lowest ad lib energy intakes on the far right are at extremely high protein 50%, extremely low carb of 10%, and then you exactly flip-flop those to low protein of 10% and high carb of 50% to get the highest ad lib energy intake. Okay, Raubenheimer and Simpson made another discovery. The more ultra-processed your diet is, the lower it is in protein. It's pretty much just a straight line going down. That makes a lot of sense, right? Maybe this is why ultra-processed diets perform so poorly when it comes to health outcomes. And you know that Americans eat mostly highly processed. The majority of our calories are highly processed. It's the maybe 5% of our calories that are minimally processed. I have this great photo from the 70s. You ask yourself, well, what the hell happened in the 70s to kick off this obesity epidemic, right? Before this, people were eating meat and potatoes. That's what people ate. You ate meat and potatoes. Think about how much sugar, flour, and oil you had to dump into this crap to make it shelf stable. This is, you're looking at the birth of the obesity epidemic right here. This is basically what it looks like. This photo really sums it up pretty nicely. Speaking of the grocery store, Robinheimer and Simpson made an economic discovery. They graphed out the price of every food in the grocery store based on macronutrient. The more protein in the food, the more expensive it is, period, linear. And we know this instinctively because protein is the hardest to produce. It has the lowest profit margins. It's the most expensive to manufacture. Protein has all these logistical challenges. It's for refrigeration and spoilage and transport, and protein's least convenient. It's the least portable, and it requires the most cooking. There are all these economic and logistical reasons why protein's the hardest thing to get. And that is why you can make a map of obesity and a map of poverty and overlay them, and they just line up exactly. It's pretty sad, but there are huge economic factors here. Okay, what would happen to you if you actually ate a high-protein diet? Well, let's not start off with humans because maybe it just kills you, right? Let's start off with some rats. These study people took a bunch of rats, and recall that rats are self-selecting for about 23% protein, and they just dumped 50% protein on them for a big chunk of their lives, just arbitrarily. And they did this at the expense of carbohydrates, which is exactly what you'd want. They basically gave them 50% protein at the expense of carbs. And what happened to these rats? Well, they tracked everything. These rats were they were super rats. They were ripped and jacked. They had the highest lean mass, lowest fat mass, lowest insulin, lowest triglycerides, lowest glucose, did the best on a glucose tolerance test, lowest amount of liver fat. The authors concluded that tripling the protein intake did not produce any adverse effects on the renal and hepatic functions, on oxidative stress, or on calcium balance. On the contrary, exchange of carbohydrates for protein was beneficial regarding body composition, basal triglycerides, glucose, leptin, insulin, blah, blah, blah. They basically figured that you could treat or prevent any case of obesity or metabolic syndrome with this protein for carbohydrate substitution, which of course is 100% true. Okay, let's move on to some human obesity studies now that we know the rats survive. And I have a spoiler alert for you. Every single human obesity study you will ever look at, ever at all, period, in the history of medical literature, the more protein people ate, the better, always, completely. Like there's no exceptions. But we'll just talk about some anyway. Here's an ad lib obesity study, 12% versus 25% protein. Of course, the high protein group crushes the low protein group. Look at the intra-abdominal fat going down on the high protein group. Here's 1.6 grams per kilo versus 0.8 grams per kilo. The high protein group lost 53% more body fat on the same number of calories. What? I thought it was all about calories. Well, it's clearly not about protein calories. Okay, here's a study, ad lib human obesity study, 15% versus 30%. Of course, the high protein group just crushes the low protein group. They lost way more weight, way more fat, and had lower hunger scores the entire time, which is pretty magical. 16% versus 27%, of course, the high protein group wins. This is an interesting study. They took pregnant women, tracked their macros, and ultrasounded the amount of abdominal fat on their fetuses. And they did this because we have an epidemic of gestational diabetes and fetal macrosomia and C-sections in babies being too fat. Sure enough, there's a carbohydrate effect. The more carbs you eat, the fatter your fetus is. There's almost no fat effect at all. The fattest and the thinnest fetuses were at about 40% fat. That's starting to look familiar, right? And then it's all about the protein. There's just a huge linear protein association where the higher the protein, the thinner your fetus was, and the lower the protein, the fatter your fetus was in a purely linear fashion. And if you eat a high protein diet, even your offspring comes out ripped and jacked with a six-pack, pretty much. So here's a study in pre-diabetics, 15% versus 30% protein. Of course, the high protein group had the highest lean mass, lowest fat mass. But what the high protein group had was a 100% pre-diabetes reversal rate. And the authors said, wow, to the best of our knowledge, nobody's ever gotten 100% pre-diabetes reversal rate doing anything. So that's kind of cool. Here's a study in diabetics, 15 versus 30%. It was only 5 weeks long, but the high protein group had way more weight loss, fat loss, A1C, triglycerides, blah, blah, blah. Here's another study in type 2 diabetics. These authors realized when we feed protein to diabetics, their blood sugar's better, 15 versus 30%. The high protein group had 40% lower glucose area and a huge drop in A1C. Okay, there's a problem with protein. The problem with protein is we're all afraid of protein. And we're afraid of protein for no good reason. There's nothing to be afraid of. All right, here, is everybody familiar with Marty Kendall, the optimizing nutrition guy, right? Marty Kendall, this guy's awesome. All the food insulin index data, the micronutrients. Here's Marty's graph of food insulin index versus protein. You can clearly see the more protein you eat, the lower your food insulin index. Here's glucose score versus protein, same thing. The more protein you eat, the better. Here's Marty's graph of micronutrient density, which is fascinating. He says of all the nutrients, protein has the highest correlation with nutrient density, and he sees the highest protein at 45% seems to give you the very highest nutrient density, which is really interesting. Okay, hold on a second. Aren't we all protein addicts? This is Proteinaholic, written by my arch frenemy, Garth Davis, the low-fat vegan bariatric surgeon. And he says we're obsessed with protein, and protein's too high, and it's just killing us, and that's basically the problem. Well, here's the Health ABC study looking at actual macronutrient intakes in American adults aged 70 to 79. And you can see these people are eating 38 grams of animal protein a day, 28 grams of plant protein a day. That's 66 total grams of protein, which is way below the world average, which is already too low for economic reasons. And instead, these people are eating 247 grams of carbohydrates a day. And I would say maybe they're not proteinaholics as much as they are carbaholics. Okay. Here's some high protein studies. These people ate 3.4 grams per kilo, 1.5 grams per pound. That's around 250 grams of protein a day, 39% of calories. There are some doctors who say you can't even live with protein at 39% of calories. It's totally wrong. What happens? You're ripped and jacked. You have the highest lean mass, lowest fat mass, lowest body fat percent. All your labs are awesome. Here's another study. Again, 3.3 grams per kilo, 1.5 grams per pound, 250 grams a day. Again, 39% of calories. They tracked everyone's labs before, during, and after. It was a one-year crossover. Everybody's labs were great, and this was totally awesome. They had body composition improvements. Imagine that. Here's some crazy Korean bodybuilders who ate over 400 grams of protein a day, 4.3 grams per kilo. They tracked all their labs. Everything was perfect. Their blood sugar was normal. They had insulin level of 2, which is pretty awesome. Okay, here's a protein overfeeding study. They took these healthy people and just dumped protein on them until they got up to 45% of their calories. And no, they did not die with protein at 45% of their calories and 4.4 grams per kilo. Instead, what's really interesting is they looked at their diet before, looked at their weight and their body composition before, dumped what ended up being 800 calories of extra protein on top of their diet, and their fat mass went down. That's right, 800 extra calories and their fat mass went down. Does that invalidate calories in, calories out? No, it doesn't, because their lean mass went up and their energy expenditure went up, but their fat mass went down. So what that does to calories is make them basically stupid and pointless when you're talking about protein. Okay, what about kidney function? We all think that when you eat too much protein, your kidneys just dissolve. Is that really true? No. There's no case reports of that ever happening. It just literally can't happen. Here's a letter to the editor of a nephrology journal. They've never seen a case report of high protein hurting anybody's kidneys. It's totally mythical and a bunch of garbage. Well, what happens if you have chronic kidney disease? Is it really true that if you have normal kidneys, protein's fine, but the second you have a kidney problem, protein's terrible? No, that's basically crap as well. Here's a meta-analysis, and these are the different causes of chronic kidney disease, mostly diabetes and high blood pressure. In none of these has protein restriction ever been shown to be of any benefit whatsoever, ever, period, at all. With one tiny exception, this little 7% of chronic kidney disease, which is primary glomerular disease, women did not benefit at all from protein restriction. Men had a tiny microscopic 3% improvement. So 3% of chronic kidney disease maybe has a 3% improvement. But here's another study that found no significant difference, and here's another study that graphed out protein restriction versus no protein restriction in kidney disease, and they found no borderline or no difference. Here's another study that graphed that out, and they found no difference. So it's basically borderline mythical that protein restriction is of any help at all for anybody. Okay, what about bone health? Okay, every self-respecting vegan will tell you that eating animal protein will just melt your bones. It is so acidic, right? We've all heard, I read that on the internet. It turns out recommendation to intentionally restrict dietary protein to improve bone health is unwarranted and potentially even dangerous. Why would it be dangerous? Because it's quite clear the more protein you eat, the higher your bone density in a perfectly straight line. Your bone is 50% protein. It's 50% minerals and 50% protein. It's not just a stick of chalk. So the more protein you eat, the better. Here's the Framingham osteoporosis study. The more protein these people ate, the better the bone density, especially animal protein. Interestingly, when people lose weight, their bone density goes down because they're lighter. Here's a study of 25% versus 12% protein. You had higher bone retention in the high protein group. So you lose less bone when you lose weight. Okay, what about gout? We all know that if you eat muscle meat and a bunch of protein, you're just going to immediately raise your uric acid levels and get a gout attack. I saw that on WebMD. Turns out that's a giant load of crap. Here's a study of a bunch of men with high uric acid levels and gout, and they put them all on the Atkins diet where they dramatically increased their intake of muscle meat and protein, and everybody's uric acid got better and everyone's gout went away. And the authors concluded that, oh, hey, actually a high protein diet is awesome for gout as long as it's low carb. Okay, what about ketosis? All right, so I've decided I have to be in ketosis for every second of the rest of my life, all the time. I don't know why, don't ask me, but I just have to be. Can I eat protein? And the answer is yes, you can eat a ton of protein. Here's over a gram per pound. Here's over 1.25 grams per pound, 221 grams a day. These people are in continuous ketosis. No problem. Eat all the protein you want. Here's a bunch of, this is a meta-analysis, and in all these studies, they ate at or over 1 gram per pound. They were all in continual ketosis. Here's a meta-analysis of 23 studies looking at beta-hydroxybutyrate blood levels, as well as grams of carbs and protein eaten, and they graphed them out with beta-hydroxybutyrate going up on the top row, so you could immediately see if there was a visual correlation between ketones and carbs or protein. Of course, there's a huge inverse correlation between ketones and carbs, but there's no correlation at all with protein intake. Same data graphed a different way, protein going up on the bottom row, no correlation with ketones. Eat all the protein you want. Here's a ketogenic diet study. These people ate 30% protein. They were in continual ketosis. They had super low hunger scores. They did awesome. Here's a really old-fashioned ketogenic diet study, and they had these 125-pound women, and they found that at 100 grams of protein a day, they were in continual negative nitrogen balance, but at 150 grams a day, they were in continual positive nitrogen balance, yet they had the same identical ketones either way, and the authors concluded, hey, if you're a 125-pound woman, you'd better eat 150 grams of protein a day instead of 100 to maintain positive nitrogen balance. Okay, what about the G word, gluconeogenesis? We've all heard that protein turns into glucose. I thought that, I didn't know. I thought protein turned into glucose. You didn't really learn this in medical school, right? It turns out that protein does not raise your glucose. I like the title of this study, which sums it up. Dietary proteins contribute little to glucose production even under optimal gluconeogenic conditions in healthy humans. They fed these people a bunch of protein. What happened to their glucose? Absolutely nothing. More studies. 106 grams protein, glucose did nothing. 132 grams of protein, glucose did nothing. 132 grams of protein, again, glucose, nothing. 160 grams of protein, glucose did nothing. Here's another study. Amino acids went up because they fed them protein, but what happened to glucose? Protein versus water, no difference. Didn't go up or down at all. Here's a study in type 2 diabetics. This person's blood sugar was 160 the whole time. They ate 136 grams of protein. Nothing happened to glucose. Here's another study. Rate of glucose appearance in type 2 diabetics, protein versus water. Which one's protein? Which one's water? I didn't even put the legend on this graph, so we'll never know. We really won't know. It doesn't even matter. They're exactly the same. Okay, so yeah, that's basically mythical. Okay, what about satiety? Now, satiety is huge. Satiety is so crucial. This is how protein leverage works, right? Satiety powers protein leverage. Let's look at some studies. 25% protein versus 14% protein. This is a satiety study, and to make it more interesting, they split each group into two subgroups, eating 3 times a day versus 6 times a day, wondering if eating more frequently was better for satiety. Spoiler alert, eating more frequently was significantly worse for satiety across the board. But anyway, the highest daily fullness, high protein group, eaten less frequently. Lowest desire to eat, high protein group, eaten less frequently. Lowest daily hunger, high protein group, eaten less frequently. Are we seeing a pattern here? Here's another satiety study, 25% versus 14% protein again. And look at the cravings here. Obsessive thoughts of food, less than half in the high protein group. Late night desire to eat, less than half in the high protein group. That's crazy. That's pretty awesome. Here's measurement of direct hunger scores with the 3 macronutrients. Normal subjects on the left, obese subjects on the right. Protein is by far and away the most satiating macronutrient. Fat is second, although interestingly, in obese persons, fat is far less satiating than in normal people. Okay, here's a preload study. Preload study, you give somebody a snack, like an appetizer, and then 2 hours later they hit the buffet and eat as much as they want, and you measure it. Protein's the best preload by a wide margin, much better than carbs, fat, sugar, or a mixed preload. Worse is a mixed preload with sugar and fat together. You eat a donut, and 2 hours later you're going to clean out the buffet, pretty much. This is lean women, macro preloads. Protein's the best one, alcohol's the worst one. That's kind of interesting. Okay, let's talk about weight loss maintenance, right? This is a huge big deal. Anybody can lose weight, just stop eating for a couple days. But how do you maintain long-term meaningful fat loss? This is really the holy grail, right? Protein is fantastic for weight loss maintenance. Here's a study where they took a bunch of people who just lost weight and randomized them to eat an extra 48 grams of protein or not per day. And that's about the size of a super large chicken breast. It would be like if everyone in this room just lost a bunch of weight and I flipped a coin and I said, this half of the room, you have to eat a large chicken breast every day, 48 grams of protein. Here you go. I'll give it to you. Just eat it right now. This half of the room, forget I even said anything. And then what happens? 4 months later, you have 50% less fat regain on the high protein group and higher lean mass and lower hunger at the same time. So you maintain your weight loss with higher lean mass and less hunger at the same time, just by eating extra protein. Here's a meta-analysis of a bunch of studies that basically showed that the higher the protein intake, the more fat loss you maintain in all of these studies. There was a significant effect on triglycerides and insulin as well. They found that if you could keep your protein 5% higher by the end of the study, you had triple the fat loss than if you didn't. That's protein leverage right there. And of course, there's a significant effect on triglycerides and insulin and other markers. Has anybody heard of the National Weight Control Registry? This is a giant database that anybody can be entered into if you lose 30 pounds and keep it off for a year, right? National Weight Control Registry, long-term successful fat loss. You lose 30 pounds, keep it off for a year, you can be entered into this. And people in this registry are all over the board on carbs. It's like high carb, low carb, high fat, low fat, lots of exercise, no exercise, lots of calories, no calories. People are doing everything you can think of with carbs, fat, exercise, calories. There's one thing that all these people in this registry have in common. What is that one thing? Bam, protein's 18 to 90% of this whole group when the human average is 14 to 15%. These people basically dragged their protein up almost to a hunter-gatherer stage and had long-term meaningful fat loss, right? And of course, protein leverage states that if you raise your protein 4%, you're going to eat 410 less calories a day, which is, that's pretty significant. Okay, what about in a low-carb setting, right? We're all low-carb fans here. Everybody in this room is a low-carb fan. So what happens when you specifically look at higher versus lower protein in a low-carb setting? This pretty much applies to all of us. Well, here's a weight loss maintenance study. They took people who had just lost weight and randomized them into high-carb, low-carb, high protein, low protein. So there were 4 different groups. The only group that maintained their fat loss was the high protein low carb group. The low protein low carb group in red there regained just as bad as the high protein high carb group. And of course, the low protein high carb group was almost as bad as the control groups. They were just eating donuts, I guess. But the bottom line is protein is huge. Here's another study, and this looks at exactly what we here would want to know. What happens when you look at an isocarbohydrate, isocaloric diet that's either 15 or 30% protein. Basically, 2 identical low-carb diets with identically low carbs and the exact same calories. Just one group got 15% protein and more fat. The other group got 30% protein and less fat. What do you think happened here? The high protein group just crushed the low protein group at everything you could measure. Weight, body fat percent, insulin, HOMA-IR, triglycerides, HDL, hunger scores, emotional eating, anything you could measure, the 30% group beat the 15% group. How do you get to 30% protein on a low-carb diet? That's equal grams of protein and fat. Anytime you're eating equal grams, like if I ate 150 grams of protein and 150 grams of fat per day, I'm automatically at 30% protein, 70% fat on a low-carb diet. So basically, you get to 30% by eating equal grams of fat and protein. Here's another study. This is an isocaloric low-carb study as well. Identically low-carb, identical calories, 18% protein versus 34% protein. What happens? More than double the lowering of insulin, HOMA-IR, and triglycerides on the high-protein group. This is not small, people. This is like a huge big deal. And again, 34% protein is protein grams slightly higher than your fat grams every day, which is basically the way I'm eating. Okay, what else do we have? Overfeeding. You cannot make someone fat by overfeeding them protein. Their energy expenditure goes way up, their lean mass goes way up, but their fat mass doesn't go up at all. And I don't know about you, but I like energy and I like lean mass, so this is a good thing. Here's a graph of waist to hip ratio versus protein intake. It's a straight line going down. That's kind of interesting. The more protein you eat, literally, the lower your waist to hip ratio. Oh, and finally, sorry, vegetarian women, because omnivore women have a higher muscle mass index, and if you're a woman, the more animal protein you eat, the higher your muscle mass index. Okay, protein is sort of a U-shaped curve though, right? If you get really, really high protein percent, you get super lean. The cost of weight gain, this is a graph of the cost of weight gain versus protein percent. You crank your protein up really high, you get super thin like a bodybuilder. But there's a flip side to this. If you can get your protein really low, down to about 5%, you also get very, very thin because the cost of weight gain goes way up. This is how low protein vegan diets work. If you can get your protein this low, this is 30 bananas a day, right? 5% protein. This is the Kempner rice diet. This is the McDougall starch solution. This is the potato hack. You get your protein really low, you lose a bunch of weight because the cost of weight gain goes through the roof. Why is this side bad? Because you have low lean mass, you have osteoporosis, osteopenia, sarcopenia. You have low vital mass, which is the weight of all your organs, including your heart and your brain. I don't know if you really want your brain to weigh less. What's interesting is the very, very bottom of this curve is where the U.S. has rolled downhill like a marble to the very, very lowest point, where it's the easiest to get maximally fat. This is the exact same protein percent we put in obesogenic rat chow for the reason that it's the most efficient fattening. You get your protein here, and you get the fattest, the easiest. And it makes sense from an evolutionary perspective that now that we're surrounded with unlimited energy, we would just bottom out at the very most efficient fattening place. Now, I've made all these graphs of protein versus energy, and you can find them on my website. It's grams of protein versus grams of non-fiber carbs and fat. And when you graph out all your foods on a protein-energy ratio, some really cool stuff just pops out at you. First of all, meat and eggs and grains are fantastic, right? Well, we kind of already knew that. Sugar, flour, and oil, super terrible. We knew that too. Other things that pop right out at you. Ground beef is awesome, any percentage. Here's all your percentages of ground beef, spectacular food. Here's all your grains, total garbage. The very best grain, oatmeal, pretty much not worth eating. Worst grain, rice, it's total crap, right? Grains are crap, but we already knew this. The summation of animal foods is higher than the summation of plant foods. I think the carnivores figured this out. The worldwide hunter-gatherer average is higher than the standard American diet, 2 or 3 times higher. I think we knew that too. Okay, I'm almost done. I just have like 1 or 2 more slides and one more concept to get across. And this concept is really mind-blowing. At least I had no idea that this was even happening. So plants create all of our food. Plants are at the base of the food chain, right? Plants produce all our protein, plants produce all our energy. They pass it up to herbivores, and they pass the same protein and energy up to carnivores. Plants are getting nitrogen and minerals from the soil, and then all their energy from carbs and fats stored as carbon that they get from carbon dioxide in the air plus sunlight. And they pass this up to herbivores and then carnivores. So your plant is getting the carbon for energy, carbs and fats, from carbon dioxide in the air and sun energy. And it's getting all the nitrogen and minerals for protein from the soil. So there's this sort of air versus soil thing going on in your plant. There's basically a carbon or energy to nitrogen, which is protein and minerals ratio, or sort of a carbon to nitrogen ratio in your plants. Where am I going with this? Atmospheric carbon dioxide has doubled in the past couple hundred years. What happens when you grow a plant today and doubled CO2 versus a couple hundred years ago? I'll tell you what happens. You increase the non-structural carbohydrate to protein ratio by 54.5%, which means that every plant food on Earth has 50% more non-structural carbs per unit of protein. That's why every single animal on Earth is slightly fatter now than it was 200 years ago. Even insects are fatter than they used to be. Talk about an obesogenic food environment. You just walk outside and eat a natural plant food, and you're automatically getting more carbon energy and less nitrogen and protein and minerals. There's nutrient dilution in the form of minerals. Carbon's gone way up. Minerals and protein and nitrogen has gone way down, even if you just walk out and eat a natural food. And then it gets worse because plants store energy. And we preferentially eat at the part of the plant that stores the energy, the fruit or the tubers, right? We're trying to get this energy. And then we cultivate it to max out the energy yield. You want a potato the size of your head, right, with tons of energy in it. And then we refine and process it even more. And by the time we get done, what you're left with is so high in energy and so low in protein and minerals that it's just absolutely ridiculous. And that's why every single thing you eat is just massively obesogenic in today's environment. The only way you can fight this is to go out of your way to eat as much protein and minerals as you possibly can to get around all this energy dilution. Okay, sorry, I ran a little bit over, but that's the end of my talk.